All right, so today we're going to learn about something called the buoyant force. And I sent everybody a worksheet via email and asked you to print it. So I hope you have that ready because you need to print it and follow along. Okay, so here's a setup. Here's a beaker of water. This thing is a force sensor. You've used it before. It measures the force, string, and a solid sphere. All right, now first thing we're going to do is tear the force sensor. Okay, so you notice the sphere is not touching the water. It's just hanging from the string. So now we're going to measure. All right, here we go. So we're going to record the weight of the okay. Now, I'm not going to use these numbers. I'm going to use numbers I used a little while ago. All right, so, but it's okay. You'll still see what's going on. All right, so here it says the force is, now the minus sign is because it's being pulled, so don't worry about that. So here we have 1.185. Well, the last time I did it, I have 1.16, so I'm going to use that because I already calculated everything. So the weight, (1.16 newtons). All right, now, so what I want you to do is draw a force diagram and compare the weight of the sphere to the tension. So you can do that. So pause your video and do that. All right, so the force diagram, you have your tension and you have your weight. So the tension equals the weight. No kidding. 1.16 newtons. All right, now watch. So watch what happens. Okay, so you have to watch two things. You want to watch this, the force, okay, and you want to watch what's going on here. So basically, I'm going to submerge the sphere into the water. So I've got to get this going again. Okay, so watch what happens to that. So I'm going to lower it until it's completely submerged. Okay. Now what happened? What happened to the reading on the force sensor? It decreased, right? It decreased big time. So again, I'm just going to use my measurements. And you can see it here, right? So we were down like 1.16. Now we're much, much less than that. Here it's like 0.5. I'm not going to use that. But it went down, okay? So what I did earlier, okay, so this is out of the water. Okay, now submerged, I have 0.485. That's submerged. Okay, so obviously what's going on? So I mean the weight was 1.16 newtons above the water. Then we put it in the water, and the weight or the tension decreases. So that kind of implies there has to be something pushing up on the sphere, right? Okay, so what is the change? So what's 1.16 minus 0.485? Well, it's about 0.675 newtons, okay? So that minus that is approximately that. I'm not worrying too much about significant figures. Okay, now, the sphere is still in equilibrium, correct? It's not accelerating. So, so please draw the force diagram. So pause your video and draw the force diagram. All right, so now, so there has to be an additional upward force. All right, so there's the tension, and now there's some additional force. We're going to call it the buoyant force. You'll see why in a minute. All right? So there has to be this new force pointing upward. And we'll call that the the buoyant force. Okay? All right, now I want you to make a prediction. So I'm going to lower the sphere deeper into the water. And let's see if this force reading changes much or at all. Okay? So here we go. So what do you notice? Did it change? No, it didn't. I mean, it's hard to tell, though. It's going so rapidly, all right? Okay, so in other words, this reading here, or this delta at 0.675 newtons, it's independent of depth. Once that sphere is under the water, the reading doesn't change. Okay? All right. So what we want to do now is we want to... okay, so this sphere displaced some water, correct? It took up the space of some water. So what we want to do now is we want to measure the weight of the displaced water. Okay? The weight of the displaced water. Well, how do you do that? Well, you know, if you know the volume of this, I mean, here. So density is mass over volume, so therefore the mass is the density times the volume. Okay, so we can figure out the volume of this thing. All we have to do is measure the diameter, right? And then figure out the radius. And the volume of a sphere is 4/3 pi r cubed. Okay, so we can do that. And then we know that the density of water is 1,000 kilograms per cubic meter, right? Okay, so all I'm saying is that we can calculate the weight of the displaced water, right? Okay, the weight of the displaced water. And I already did that for you, okay? And when you do that, the weight of the displaced water, that's the equal sign, right, is 0.675 newtons, approximately, okay? So, what do you notice? When we put this thing in the water, there was this new additional upward force, the buoyant force. And we calculated it, right? We calculated what it had to be, 0.675 newtons. Then, when we calculated the weight of the displaced water, fluid, it was exactly the same thing. So what does that imply? It implies that this buoyant force is equal to the weight of the displaced fluid. But also what we learned is that that buoyant force, it doesn't change. As long as this thing is completely submerged, I don't care where this thing is located. As long as it's completely submerged, the buoyant force doesn't change. All right, thank you. Okay, that's enough.